Yeah, I know I have been absent for too long, sorry, I am working on a lot of stuff at once, but now that I'm here, let me show you how to light up your shaders. Last time I explained the shaderlab structure, how the data is input, transferred and output on a shader. Today I will explain how you can process diffuse lighting on both baked and real-time types. I will use my favorite VRChat base for the examples because I can and I want. Now, I apply a new shader to the materials on the avatar, with its corresponding textures of course. First of all, I will teach you the most simple light you can process on Unity, a directional light. A directional light is just a sun, it doesn't have position, so the only thing we need from it is at what direction is it looking at. First of all, and very important, we will add a tag on the pass. This tag will be light mode equals forward base. That will provide the necessary information for basic lighting on the pass. Now on the input structure, we will need the normal of the vertices. For that, declare a float 3 as the normal, and for the output structure, also declare a float 3 for the resulting normal. Now to the vertex program, if you return the input normal to the output normal, the shader should look like this, but wait, that is the raw normal, we have to orient it along the 3D scene the model is in. For that, we can use the function named UnityObject-to-world-normal, to get it. You first need to include the file unitycg.ginc after the vertex and fragment pragma. You can find the source code of this file and many others on the link in the description. Now we can calculate the lights. We can do it either on the vertex or fragment program. In my case I will do it on the vertex program because it will help the performance a lot. So I'll create a new fixed 3 variable on the output structure to pass the resulting light to the fragment output. Since this one is a color and not a vector, its type will be color. As I said before, we only need the light direction for directional lights. This variable's name is _world space light pose 0, and the magic function that will calculate the light will be the dot product. This function returns the distance between two vectors. Here you have the whole function if you want. Now we apply the function to the output variable. Why does it look black, you say? Well, stereo has a smooth brain and didn't add a directional light on the scene. Here is the result. And to get its color, you just need to declare the variable _light color 0 if you haven't included the lighting.cginc file. Then multiply it by the dot product. And finally make sure to limit the negative values from the dot product to avoid unwanted results. Looking fine and smooth, but what if you wanted to use lights with position? Such as point lights. On the forward base pass you can shade a directional light and 4 additional point lights. There's a second pass named additive, where you render extra lights on the scene. But I'm going to keep it basic. The parameters we will need for the positions will be Unity_4light pose x0, y0 and z0, for the attenuation Unity_4light r10, and for the colors Unity_light color as an array. You don't need to declare them. We will need to get the direction of each light and its attenuation. The attenuation, as you might expect, fades the light intensity the further away it is from the vertex. Directional lights don't have it because, well, preferably, point lights are calculated on the fragment shader, so I won't complain if you do it on the vertex shader. First off, the attenuation. As you saw, there are 3 variables for the positions, but 4 point lights. That's the thing, each variable is not a light position, it's an axis for each light position. This is helpful to calculate the attenuation. To make the lines simpler, I'll assign the positions to a shorter name variable. After that, we will also subtract the world position of the vertices to the light position to get the distance it is from the object. To get the world position of the vertices, you can create a new float 3 output coordinate variable. But just as the world normal, if you are going to calculate all the lighting on the vertex shader, You don't need to, you just replace the O.structure output to what type you declared it as on the output structure. The calculation will simply be, multiply unity_object to world, and the input structure vertex position. Pretty much like this. Now we add the previous variables below all this stuff and proceed to calculate the attenuation. That will be, all three positions multiplied by themselves then summed. Then take the maximum between this and 1 raised to the power of -6 or 0.000001 if you want. Save the result on a float-4 variable, then multiply this by the point light attenuation we got before, then add 1. After that, divide 1 by this and finally compare the maximum between 0 and this. Also multiply it by the reciprocal square root of the previous result. Now we have a float-4 as the attenuation for each light on its 4 axes respectively. Now the easy part, to get the direction we need to break down each light position. As I said previously, these are constructed of each light's axis on each variable, so we just need to separate the values. That can be done by creating 4 float-3 variables, like this. And after that, normalize them to get the direction. The normalize function scales a vector from whatever range it has to a range from -1 to 1. It only works for 2D or 3D coordinates. Don't try it on any other data. Here's the whole function. As you can see, it takes the length by making some Pythagoras black magic and divides the vector by it. Well, now we finally have the direction and attenuation. What's left is to do the same as with the directional light, calculate the dot products, limit it so it doesn't give negative values, and multiply it by its corresponding color, only that now we'll also have to multiply it by its corresponding attenuation value. And now, last but not least, the light type that you should always use on your shaders, the global illumination or light probe. It's not dynamic, but apart from being the best, if not only option to light up dynamic objects without having to calculate intensive amounts of point or directional lights, it's a very optimized lighting method. This one can be calculated on the vertex shader with no problem, so just add this function to the output light result. This function shades the spherical harmonics. What is a spherical harmonic, you say? What is really important is that the W-axis always has to be 1, or else you'll get wrong results. And now, to combine the lighting you calculated on the vertex shader with the one on the fragment shader, you just need to sum the output light variable we declared on the vertex output structure. And to finish the shader, we'll create a new fixed 4 variable for the main texture if you haven't yet, and then return the texture multiplied by the light. Here's the result, looking fine I must say. So that's everything you need for basic lighting on your shader. Now if you don't mind me, I am going to chat to hug every now and then I find on the lobbies. Goodbye, and don't forget to watch Made in Abyss only if you are willing to have an existential crisis for the next 2 days.